Well, hello everybody, and welcome to another educational video in the realm of seal evaluation workflows. And what we'll do in this video is talk a little bit about seal risking workflows for deep water stratigraphic traps. So hopefully that's of interest to a lot of folks. Stratigraphic traps, obviously over the last 20 years or so, deep water strat traps have been kind of a major exploration focus. Um, some major success, some significant real play opening discovery wells. I think the Jubilee well in the Tano Basin about 20 years ago, and then about 10 years ago, the Lisa well drilled by ExxonMobil and partners offshore Guyana really opened up a lot of follow-on potential, and those companies involved in those have obviously done very well compared to their peer groups. But at the same time, there's also some very high cost failures. These are expensive wells. So, things like, look at the Raya well drilled by Total offshore Uruguay. It was the deepest water well, came up dry, and ExxonMobil at the same time that they drilled the Lisa well in Guyana, they drilled an expensive well offshore Liberia, deep water strat trap, the Meserata well that didn't come up with anything. So being able to differentiate in risk is very important. And in my view, I think based on company activity, we're going to continue to see strat traps being drilled, and we will see some play openers, and we will see some high cost failures. So you want to be in the right wells to succeed. So components of charge are obviously important to risk, especially if you're in unproven basins. But that's really in my view, a play scale risk is really not so much a differentiator of prospects within a block or within a basin or within even a set of basins. And at the same time, what we tend to focus on a lot is kind of the reservoir architecture of these prospects. So we make beautiful maps of the detail of reservoir architecture of these deep water strat traps, but we really don't have wells that truly fail because they fail to encounter a reservoir. So the thing that really sets this thing apart is retention, and within retention, and we'll talk about that, is seal. So in my view, if you do a good job of differentiating your portfolio based on seal, and that's really a differentiator because wells fail or succeed because of that, you're going to be in a better place. But you very often don't see those seal workflows being applied. They're not that well established, not that well articulated, not well published. And it requires a bit of more of a subtle eye to think about seal than it does reservoir. So in this video, let's kind of touch upon it a little bit, and hopefully by the end of it, you'll feel a little bit more comfortable with how you might go about doing seal evaluation in a portfolio sense. So retention, as I said, is really what is the key risk. And then retention, again, what's the definition? It's the ability for connected volumes of hydrocarbons to backfill from a crest. So they go to a crest and then they backfill. That's what retention is. Okay. And retention is made up of two components. One is called trap, and that's the geometry of the container. So it's your ability that you can make a map of that and your confidence that that structure is there upon depth conversion. Now, I would argue that trap is very rarely a risk when we're dealing with strat traps. They're not that hard to map, in all honesty. And in most cases, we have 3D seismic coverage with fairly benign sort of depth conversion challenges. So trap is not really typically a problem with these stratigraphic trap types. But the component of retention that is the key risk factor is seal. It's the rocks that surround the container. Okay. So seal, and again, when something fails for seal, it does it by one of two ways. And again, I use these words very consistently, and therefore I need to apply a definition. And there's spill. Spill is the escape of hydrocarbons through a bypass pathway. And that bypass pathway, by definition, is the hydrocarbon-water contact. So that is the spill point in the case of failure. So what fails is if I have a spill point that's located at a depth shallower than my risking minimum column height. So it's very important, again, when we think about seal risking, that we define the risking minimum and that we use that risking minimum to define a minimum in our column height distribution. If you don't do those things, then you might as well not bother doing risking at all because it's kind of pointless. Now, the other way hydrocarbons escape is through what I call leak. So when I use the word leak, I specifically mean escape of hydrocarbons near the crest as the buoyancy pressure is exceeding the either mechanical or most typically, as we demonstrated in a previous video, the capillary seal capacity of my trap. So risking minimum is important to define, and I would suggest that that is a column height. So let's say I have a stratigraphic trap, so the classic distributive to lobe, weakly confined to distributive system here, kind of coming down a slope, lower slope to base and floor, and these are 50-meter contour intervals. So let's say I use a 50-meter risking minimum. That means what I'm risking is this. So the seal envelope for risk is shown here in red. I am not risking the entirety of the feature, okay? And again, this is something that I see go wrong a lot, is that people double dip on risk and the column height distribution they use in their assessment. So just be aware what you're risking against. That is what you need to evaluate for seal, okay? So what components of seal are there in stratigraphic traps? Well, there's 4. Okay, there's 4 seal risks that you need to articulate, that you need to risk, that you need to have discussions around, and they're all independent of each other. So you need to multiply the chance of adequacy, and therefore seal is a major risk. Okay, so again, that's my perspective. That is your differentiator in prospect. It's not reservoir, it's not charge, it's not trap, it's seal. Okay, so what are the 4 components of seal to think about? Well, this is the one that everybody is familiar with, is top seal, right? So again, for a 50-meter column height, that is the top seal envelope and the area that I need to risk against. Then there's base seal. Most people know about it, although in my experience, very often forgotten or ignored, and that is a seal at the base of the reservoir. The base seal envelope is always smaller than the top seal envelope, okay? Just by nature of how traps work in stratigraphic traps. Lateral seal. So for me, lateral seal is just that. It's the lateral parts of the system. Okay, so it's the edges of the depositional system. And then typically what we spend most time on is what I call dip seal or up dip seal. Okay, sometimes people call this lateral seal as well, but to really differentiate this, I call this dip seal. And that is sealing in the coeval deposits that are in the classic strat trap part of the feeder system. Right? So there's something that fed this weakly confined to distributive system, something channelized, and the up dip seal risk embraces that there could be sandy deposits in the channel feeder that connect all the way up. Right? So that's the risk. So how do I get rid of that risk? Either I erode it, that's a great way to remove a lot of risk in strat traps. If I can do that, it needs to be a bypass system, right? So I need to have bypass in the feeder system so it's backfilled with mud. Now, dip seal can also be at the other end. If I rotate the system and the pinch out is at the down dip part of the depositional system, that becomes my dip seal. So again, I have time equivalent deposits at the fringes of this system that I need to risk for updial sewer. So this is called the dip reversal trap. I like these. In general, these are much less risky for dip seal than the classic strat trap. So very common in rotated full blocks and sync kinematic settings. So those are the 4 components you need to risk. So you need to kind of consider all 4 of these. So, okay, I'm in a deep water setting. What rock types do I associate with seals? You know, what makes seals in the deep water? Well, the seals are made up of mud, which is anything with a grain size smaller than about 62 microns. And that mud can come from one of 2 places. It's either what I call detrital mud. It's derived from weathering on land, so that is clay mineral aggregates and silt-sized grains of quartz, feldspar, rock fragments, things like that. So that's the detrital mud. And then there's what I call the biogenic mud or the magic mud. It just appears out of nowhere. It precipitates down from the water column. So these are the components of fecal pellets, organic matter, hard parts of micro and macroorganisms, tests, scales, things like that give me the biogenic mud component. At a very first order, I always find it useful to articulate whether I think the seal that I'm looking at is pelagically dominated by biogenic mud or whether it's detrital mud. Why do I care? Well, it turns out that for columnite distributions, biogenic mud dominated systems just tend to be a little weaker as a seal than detrital mud dominated systems. Okay, so it influences Not necessarily the risk, but the column height distribution that you may use. Okay. So what kind of seals do I get in the deep water? Levees, right? So the fine-grained part of confined depositional systems, constructionally confined depositional systems. Levees are really interesting because very often in structural traps and combination traps, they're filled with hydrocarbons. And they connect into the main channel part. So they can actually be quite a volumetrically significant resource associated with that, and it's usually connected. So clearly it accumulates in these structural and combination traps. So vertical seal tends to be pretty good in these levees, but that lateral component is just something to be aware of, that when I'm dealing with pure stratigraphic traps, that can really make something quite risky. I don't know of many, if any, pure stratigraphic traps that are associated with large levee confined depositional systems. Because if I rely on the levees for lateral as well as up-dip seal, that gets very tricky for the bed parallel part of it. A good example is, if you want to look it up, the Flamingo well that was drilled in the Black Sea, the Romanian Black Sea. And in my view, that well really failed because it relied on seal into lateral as well as up-dip stacked levee systems that really are not very good lateral seals. When you look at distributed systems, you're looking at the fringes where I get most of the mud. And again, it's kind of similar theme to the levees, that kind of bed perpendicular. So in most cases, vertically, they are pretty good seals, and laterally, it's something to kind of keep in mind. Maybe not as tricky as levees for that lateral seal. And that's just, well, based on what you can see in outcrop, but also some very large distributive strat traps. I think, for instance, the Venus discovery in Namibia, that must rely on significant portions of kind of lateral seal into sort of these lobe fringes. So that's the lobe. One type that I think is going to become more important as we get into the next decade of exploration is stratigraphic traps that have significant components of seal by mass transport complexes. So are MTCs good seals? Well, depends what you're wasting. Right? If I'm wasting sand, then that's a sandy MTC. But generally, MTCs tend to waste slope mud, so they tend to be typically mud supported. And they're actually accident seals. If you look at threshold pressures for mercury, they can really sustain quite significant column heights in, and they're sort of good seals in all directions. I really quite like systems that use MTCs as part of the seal, but beware, they often have sand injectites associated with them. The loading of the MTCs on large distributive systems in particular can create fluidization and escape networks. So be aware of those sand injectites that exist in the Guyana-Suriname margin and in most places where we have significant MTCs. And then another typical seal that has sort of the detrital mud associated is the re-sedimentation of that mud by contour currents. So contourite deposits, drift deposits can form seals based on my experience and calibration. They tend to be fairly consistently homogeneous in composition and stratigraphy. So they're a good facies type for seal. So again, but it's good to articulate whether I'm dealing with levees, fringes, contourites, MTCs, or more of a biogenic system to really understand the risk and also what column heights I might associate it with the success cases. So, okay, that's nice, but what do I actually do with seismic data to try to risk these things? There's three things I would strongly recommend that you always do, and that I would like to see when I do a seal evaluation or a query one. And one is, just like you do with reservoir, show me flattened time slices and extractions for the seals, right? So all the different seal intervals should have those extractions. So shown here is an extraction on a coherency time slice through a top seal with an underlying reservoir prospect. Right, so the question is, can I see fractures and faults? Yeah, often these shales are polygonally faulted, so that's something that contributes to discontinuities that might not be a risk, but it's something to talk about. Fluid escape features, so in this case, there's pock marks. So again, can I explain those as not being a risk, or is that providing significant risk? And then I'm looking for these subtle bypass systems. So here's a small channel that kind of comes through here at the edge of my underlying prospect. So in some ways it might be, well, maybe that's the actual spill point, and it actually defines the spill of the success case. So it actually helps me potentially articulate why I think I see the column height that I do. One thing I'm a big fan of is when I build sequence stratigraphic frameworks is stradal termination. So I use them to build frameworks, stratigraphic frameworks, but I will also use it to really articulate the reservoir seal geometrical relationship for strat traps, right? If I can use stradal terminations, it's just a very clean way to really map the edges very clearly, rather than something that's just a subtle amplitude change or a fading of amplitude away from something. It's just not a very crisp definition. So again, query it, articulate. Is my top seal? Am I onlapping my structure? Is it draping? The base seal, very important, particularly in shown here as an example, is a wedge of stratigraphy that's sync kinematic to the tilting of the underlying stratigraphy, so it's pre-kinematic. So very often these base and margin wedges have been chased a lot, and we're still chasing them. But they very often rely on, if they unlap that pre-existing margin, that's really tricky in my experience for base seal. So you almost want these to kind of pinch out inside the mud before they actually unlap the pre-existing margin and the base seal. Lateral seal, do I see downlap or is their facies changed? So again, use these stradal terminations to really articulate the seal reservoir interface. And by doing that, you'll have a better chance of coming up with a more accurate risk assessment. And then finally, it's actually almost never done, but I think it's very important, is query the seal components of your DHI prospects, right? So all my prospects these days are at least AVO defined, so they have some amplitude that supports it. So there's a nice example of a deep water fan in the Harper Basin offshore Liberia, that there is some down dip amplitude shut off. That's always the question. Is that just lithology or is that fluid? Now, what you should do is see if you can find the spill points in the lateral or top seal or the base seal that would correspond to a shutoff here. If you can, that just gives you more confidence that the amplitude is holding together with what the spill point would be, because that's really what it is. And if it's not the spill point, then this would have to be defined by leak at the crest. So then you go, well, if this is my ultimate shutoff of amplitudes here, what is the column height that I'm building? And is that column height within reasonable range of what I would expect column heights to be for my fluid type and my seal type in this sort of system? So again, you can very quickly discount a lot of prospects that are based on amplitude because they just have column heights that are just unrealistic for typical capillary seal capacities, particularly when you're dealing with hydrocarbon vapors. So use that to query it. So those are the three things I would always do for seal evaluation for stratigraphic traps. So that's kind of it. So hopefully that was a quick tour through some of the definitions, some of the seal you need to think about, and some of the tools that you can use to risk seal. So again, in my experience, if I have a portfolio of deep water strat traps, they differentiate in a portfolio view by seal risk. They very rarely differentiate by reservoir. They very rarely differentiate by charge because that's a play scale risk. So seal is really what helps you differentiate which ones are less and more risky prospects in your portfolio. You'll never get away from, I'll never drill a dry well and I'll always be successful. But you want to be better than the competition. That's what my mentor always taught me, is you don't have to be always right as long as you're better than the competition. That's what success is. It sounds kind of harsh, but that's really the game that we're playing. So is this important in the future? Yes. This is a really nice poster compiled by Jamie Vinnels. He's done a few of these, so check him out on LinkedIn if you haven't come across. But this is kind of a summary of some of the players that are going into part of the West African transform margin and the kind of the southern part of the North Atlantic rift. And we've been here, that's where we found Jubilee and the Tano Basin plays. That's why dry wells were drilled in Liberia. We found some stuff in Mauritania, but again, this is getting revisited now with more prospects, more seismic data, higher fidelity analysis. But again, almost all of these are strat traps. And I would again argue that these genetic basins have very shared charge risk. So they don't differentiate based on charge risk. They differentiate for seal. They don't differentiate for reservoir. They differentiate for seal. So if you are looking at a portfolio and optimizing, really your seal workflows are kind of critical. So You may have questions after this about, okay, what's the minimum column height I should use? Should I always use the same one? Is it different for oil versus gas? Okay, you've kind of shown me the seismic methods, but how do you actually quantify seal risk? What column range should I use for success cases? Does it depend on the depositional setting, on the fluid type again? And how do I really integrate the DHI attributes with geologic risk? So these are all things that we tackle in our training as well as in our consulting. So if these are things that you or your team are interested in, we run a deep water school that we can do online in the classroom in the field. Like everybody else, we'll show you lots of nice reservoir, but what really sets us apart is we're not the sand and gravel school. We spend a lot of time talking about the fine grained rocks because that's the seal. So if you're dealing with exploration, that's your risk differentiator. If you're in the appraisal development world, that's your connectivity. So really, that subtlety of seal evaluation is something I think we add to the mix that a lot of others don't, in all honesty. So hook us up if you want training or if you need someone to look at your portfolio to really help differentiate the better from the worst and streamline your portfolio. We're here to help. So hopefully you enjoyed that video, and we'll be sharing some more videos on seal evaluation workflows in the near future. So keep an eye out. Subscribe to our channel, and you'll get alerted to the next video. See you on the next one.